Okay, welcome back to thermodynamics. This is the second lesson in our thermodynamics unit. Last video lesson, we talked about energy changes, what enthalpy was, and how to calculate change in enthalpy, so that's delta H, using bond energies for reactions. And today we're going to be looking at how to calculate changes in enthalpy, so delta H, using lab data through a process called calorimetry. So calorimetry is measuring changes in heat in a specific system. So a few important terms to go over before we jump into some practice questions so that we're all on the same page is the idea that energy, remember, is an object's ability to do work. And so we're measuring energy as either potential or kinetic energy. Now we're measuring it in calorimetry in the form of heat, which is a type of kinetic energy. So last lesson, when we were talking about bond energies, bond energy is a type of potential energy. So we can calculate delta H using bond energy as a potential energy, and now we're going to be using changes in temperature and finding heat to use kinetic energy to find our changes in energy in a reaction from reagents to products. So a system is an area in which we're studying. So in calorimetry labs, we often use an insulated cup or mug of some kind where we can close the system off as much as possible from the surroundings and insulate it. So in the lab, we often use like styrofoam cups or travel mugs or something that we can put the thermometer in as well to make our calorimeter, to try and separate our system from our surroundings. So the system is the part that we're studying, and the surroundings is everything else in the universe. And the best way to measure changes in energy in a reaction is to isolate the system from the surroundings as best as we possibly can so that no heat is lost to the surroundings. Now, this is pretty much impossible to do, but we can get close with good insulators. Awesome. So moving on to heat and temperature, these are the ways that we're going to be working with to find changes in enthalpy using calorimetry. So a couple quick definitions here. The difference between heat and temperature. So heat is the transfer of kinetic energy, and we measure this in joules. Versus temperature, we measure with a thermometer in degrees Celsius or Kelvin, but we're going to focus on degrees Celsius. If you need to convert between Kelvin and Celsius, the formula is here in case you need it. So our equation when we calculate heat using calorimetry is Q equals mc delta T. Now we'll break this equation down. Q, which we said earlier here, is heat. So our heat is Q. M is for mass, and it's always measured in grams. Temperature, delta T is temperature. Remember, delta is the change in. So to find delta T, it's going to be equal to the final temperature minus the initial temperature. Then the specific heat capacity, C, is measured in joules per gram degrees Celsius. So our temperature is always measured in degrees Celsius. And specific heat capacity is a special new constant that we use for different materials that basically says how much energy you need to put in to change 1 gram of a substance by 1 degree Celsius. So things that conduct temperature and heat very easily, think of metals and stuff like that, they will have a low specific heat capacity because they'll change temperature very quickly, versus other things that are better insulators change temperature much more slowly, and they require a lot more energy to change the temperature, so they'll have a higher specific heat capacity. So let's try looking at this equation here with an example. If I have 1.25 kilograms of water and it's heated in a kettle from 16.4 degrees Celsius to 98.9 degrees Celsius, how much heat did the water absorb? So here's our equation. We're solving for heat, which is Q. We're given M, which is a mass. So M equals 1.25 kilograms. Now, mass should always be measured in grams for this equation. So we're going to convert our kilograms into grams. 1 kilogram is 1,000 grams. So we're going to multiply 1.25 by 1,000. That's going to give us 1250 grams. For water, this is what we're studying. The specific heat capacity for water is 4.18 joules per gram degree Celsius. So that's a constant that you'll just sort of need to look up. Water is one that we use all the time, so you might end up even sort of memorizing it just because you'll write it out so many times. So specific heat capacity of water, 4.18 joules per gram degree Celsius. Joules per gram degree Celsius. And then delta T equal to our final temperature minus our initial temperature. So here this 98 is T final and the 16 is T initial. So to find delta T, we take 98.9 degrees Celsius and we're going to subtract 16.4 degrees Celsius. That's going to give us 82.5 degrees Celsius as our change in temperature. So now that we have M, we have C, and we have delta T, we can use our equation to solve for Q. So Q equals MC delta T. Sub in what we know. M was 1250 grams. C, 4.18 joules per gram degree Celsius. And finally, temperature is 82.5 degrees Celsius. Now, looking at the units for this is joules over grams and degrees Celsius. So these are actually on the denominator, so we can cancel out grams divided by grams and Celsius divided by Celsius. And that's going to give us our heat, Q, in joules, which is the unit that we're looking for. So that calculation comes out to 431,062.5 joules. Then we need to round to the correct number of significant figures. So here we have 3 significant figures, 3 and 3. So our final answer with 3 significant figures, we can write out in joules. So 43123 joules. 431,000 joules, or because that's such a big number, we can convert that into kilojoules by dividing by 1,000, which would give us 431 kilojoules. All right. So a few examples, if we go on to the next page, of how specific heat capacity kind of looks, is if you think about water. Water has a relatively high specific heat capacity of 4.18 joules per gram degree Celsius. So think about water in the springtime. It's very, very cold. It takes a lot of warm days before a lake would be comfortable to swim in. You'll notice often that bigger lakes with lots of water, the ice will disappear much more slowly than, when the snow leaves. And the same thing in the fall. So even in the fall, when it starts to get cooler at night, or summer evenings that are cold, water in a lake when you go swimming will feel quite warm still, because just a cool evening isn't enough energy to cool the lake water down very much. Versus if you've ever been to a beach on a sunny day, something like sand has a very low specific heat capacity, and it heats up and cools down very quickly. So in a really hot day that's really sunny, you might find that when you walk on the beach that it actually almost burns your feet and you need sandals or something because it's so hot. But then even just a few hours later, when the sun goes down and it gets cool in the evening, the sand gets quite cold and it doesn't hold on to that heat the same way that something like lake water does. So to give you an idea of how specific heat capacity sort of looks in terms of the numbers. So next we're going to look at some calorimetry calculations. Now calorimetry we're using eventually to find our change in enthalpy. So we're still looking to calculate delta H in the end, and we're going to use that Q equals MC delta T to find that. But there's sort of a few intermediate steps along the way to be able to get there. First thing we need to look at after that is looking at heat lost is always gained by another object. So anytime the temperature of one item goes down, the temperature of something else that it's in its surroundings is going to increase. Now, the amount of change is going to be different depending on the specific heat capacity of the item. So when you guys did your gizmos activity, you would have noticed that water takes a lot more energy to change the heat than the different pieces of metal that you were putting in the water. So it's not going to be halfway between. We have to use a special equation. So here is our equation. So the heat lost will always be equal to negative the same number of heat gained. So let's do an example. A hot piece of iron, okay, where the temperature is 450 degrees Celsius and it has a mass of 34 grams, is placed in a glass of cold water where the temperature is 5 degrees Celsius and the mass is 250 grams. Calculate the final temperature of the water and the iron. Note they will have the same final temperature. So here, there's a couple things that we're going to need to be able to answer this question, and that is the specific heat capacity of both water and iron. So C for iron, specific heat capacity of iron is 0.449 joules per gram degree Celsius. And C for water, we know from our last question, is 4.18 joules per gram degrees Celsius. Now you can already tell based on these two numbers that iron is going to change temperature much more drastically than the water is going to change temperature, because this requires a lot more energy to change 1 gram by 1 degree Celsius more than the iron. So our equation, heat lost is equal to the negative heat gained. So here our iron is going to be cooling and our water is going to be heating up. So Q of our iron, okay, that's the heat lost, will be equal to negative Q of the heat gained by the water. Now we also know that Q equals MC delta T. And because we don't know what Q is yet, we can calculate Q using Q equals MC delta T, because we do have information about the initial temperature and the grams and the specific heat capacity. So now I'm going to sub in this part for Q in our equation. So that's going to give us MC delta T for the iron will be equal to negative MC delta T of the water. Now what we're solving for here is the final temperature. So TF equals what we don't know. So we're going to need to break apart our delta T into T final and T initial. So we're going to do that next. MC and then T final minus T initial for the iron will be equal to negative MC, break our delta T apart into T final minus T initial for our water. TF is what we don't know, so that's going to be sort of our X value that we're going to be solving for. But everything else, this M, this C, and the I, M, C, and I, we know what all of those numbers are, so now we can sub those numbers in. So our iron, the mass of the iron was 34 grams. So 34 grams times our specific heat capacity of iron is 0.449 joules per gram degree Celsius. TF minus, and our initial temperature was 450 degrees Celsius. So that's all of our iron information. Equal to negative, don't lose that negative, careful. Mass of the water was 250 grams. 250 grams times the specific heat capacity of water, which is that 4.18 joules per gram degree Celsius. And then T final, which is what we don't know, minus T initial, which was 5 degrees Celsius. And that's all the information about our water. So now we can multiply our masses and our specific heat capacities together for both sides, and then we're going to have to multiply that into our final and initial temperatures, because this negative symbol, this subtraction, means that we can't just start multiplying everything together. We are going to have to multiply into both pieces and then solve for the final temperature. So 34 grams times 0.449 joules is going to give us 15.266 TF minus 450 equals negative 250 times 4.18 is going to be 1045. T final minus 5 degrees, which is our T initial. I took the units out just to make it a little bit easier to see as we work through this sort of algebra step. And now we need to multiply in to our brackets, expand the brackets. Don't lose the negative symbol there. So here we're going to end up with 15.266 TF minus 15 times that 450, which is 6,869.7. And then on our water side, this negative 1045 is going to multiply in, so negative 1045 T final minus, now watch the minus here because it's minus 5, so we've got negative 1045 multiplying by minus 45, so this is going to end up giving us a positive number here, so positive 5,225. So now we have expanded our brackets and we have terms that include our T final unknown and just regular numbers. So we're going to collect all of our like terms. I'm going to put all of my T terms on this side of my temperature unknowns and then all of my regular numbers on the other side. And so that's going to give us 15.266 TF. When we move it over, we change the symbol, plus 1045 TF. Equals 5225. When we move this number onto the other side, it's going to become a positive, so plus 6869.7. Okay, add them up. We're going to end up with 1060.266 T final is equal to 120,947. Divide both sides by that 1060.266. There's going to be some big numbers in this unit, but don't be afraid of that. That's okay. Divide, that's going to cancel out and give us our final temperature. We do the division. It's going to give us 11.4 degrees Celsius. So therefore, sorry about that. Therefore, the final temperature of the iron and water will be 11.4 degrees Celsius. Now, always double check, ask yourself, does this make sense? Okay, let's think back to our original information. We know that our iron is starting off at 450 degrees Celsius, and it's a small piece. It's being put in a cup of water, so 250 grams or 250 mils, which is quite cold at 5 degrees Celsius. Okay, so you're dropping it in. You want to make sure that the answer you get is at the very least between these two temperatures. If you get an answer that's less than 5 or greater than your highest temperature, the 450, then you've done something wrong. It has to be between those two numbers. Now we can also predict that based on the small mass of that and the larger mass of water, the very small heat capacity of iron versus the large heat capacity of water, that our water is going to change temperature much less than the iron is going to. So the iron is going to change its temperature more significantly than the water. So our answer should be closer to that 5 degrees Celsius than the 450, which it was. So we ended up with this 11.4 degrees Celsius. So our water's heating up a little bit and our iron is going to cool down significantly. So does this make sense? Yes. Always a good thing to double check. Okay. So how do we use this to actually calculate enthalpy? So remember, enthalpy is H. Okay, change in enthalpy is delta H, and this is actually what we want to find. Delta H is measured in kilojoules per mole. So not only do we just want, so heat, remember, is measured in joules, but then we also want to find the kilojoules per mole of a reaction to be able to find our enthalpy, our change in enthalpy. So there's 3 steps to go through in how to answer one of these questions. And you might need to kind of refer back to this a few times. But step number 1 is to use Q equals MC delta T to find our heat in joules. And this is going to be the heat of the solution, so how much the solution is changing. Then step 2 is to use the equation that we were just looking at to go from the heat of the solution to the heat of the reaction. Because the heat of the solution is like the surroundings, and it's going to be changing in an equal but opposite amount as the reaction is changing. Then once we have our heat of reaction, we can divide that by the moles to get delta H. A quick reminder there is the units for each of the different pieces we're going to be looking at. So mass is in grams, specific heat capacity is in joules per gram degree Celsius. Temperature is final minus initial in Celsius. If it's in Kelvin, convert it into Celsius. And then moles, we know how to find moles using molar mass or C equals N over V or any of those equations that we know from grade 11. So, quick note here in the lab, okay, when you're using a calorimeter, so that's the idea of using like a styrofoam cup or something to measure a change in heat in a reaction, the mass, okay, M from our equation, MC delta T, is the mass of the solution that's absorbing the heat. So you're going to have a mass of water. We assume the density of a solution is the same density as water and the same heat capacity as water, because most of it is water, okay? And that's going to be measuring this Q solution, and then we're going to convert it to find out how much is actually changing in the reaction. So heat of reaction, let's do a practice question here. We have 50 milliliters of 0.3 moles per liter copper sulfate reacting with 50 milliliters of 0.6 moles per liter sodium hydroxide. Initial temperature of the copper sulfate is 21.4 degrees Celsius, and it's going to rise to 24.6 degrees Celsius. Now, there's a key piece of information in that little chunk, and that is the word rises. So our temperature of our solution is going to be rising, which means that it's an exothermic reaction. Okay, it's giving off heat, so it's going to have a negative delta H value. And that's going to help us to check our answer at the end. Make sure we get that negative delta H value. So, because we know that if the temperature is rising, that it's an exothermic reaction, we need to end up with a negative delta H. Assume the density of all solutions is 1 gram per milliliter, so the same density as water. Also assume that the specific heat capacity of both solutions is the same as water. So these two assumptions you're going to need to make in all of these types of calculations. And all you need to do is just write, if it's not in the question, you just need to write a statement saying that those are the assumptions that you've made, that your solutions that you're working with in your reaction have the same density and specific heat capacity as water does. So the question says, determine the heat of reaction in kilojoules per mole. Okay, kilojoules per mole is your delta H of the copper sulfate. Write the thermochemical equation. So the thermochemical equation is the regular balanced reaction equation with either the heat included as a product or a reactant or as the delta H stated at the end of the reaction. To answer this question, they're long, big questions, and there's a lot of stuff in there, so we got to make sure we're really well organized. Looking back at our steps, so step 1, 2, and 3, we're going to work through each step. Step number 1 is just to find the heat of solution using MC delta E, delta T, and calculate heat in joules. So you're going to want to write out your balanced reaction equation. I find it helpful to see that at the beginning regardless, even though you don't really need it till the end. So I'm going to write that out. We're looking at a reaction between copper sulfate, so copper 2 sulfate CuSO4. We know it's a solution, so we know it's aqueous. Plus sodium hydroxide, NaOH, also a solution, so we know it's also aqueous. This is a double displacement reaction, so we're going to get sodium sulfate, Na2SO4, which is aqueous because it contains a group 1 metal, and copper 2 hydroxide, which is actually a solid. If you check your solubility rules, copper hydroxide is going to form a precipitate. It doesn't really matter for this question, but just for completeness. And then we also need to balance. So to balance it, we need a 2 in front of our sodium hydroxide. All right, let's work through step number 1. So step number 1 is using Q equals MC delta T to find the heat of solution. So our solution, we have to add up the total of everything we're working with. So we have 50 milliliters of copper sulfate and we have 50 milliliters of sodium hydroxide. So our solution, okay, total volume is equal to 100 milliliters. Okay, and this is mostly water. So even though there is, yes, a little bit of copper sulfate ions and a little bit of sodium hydroxide ions floating around in there, most of this solution is water, which is why we can assume the same density and the same heat capacity as water. So here it's mostly water, therefore same density as water, which is 1 gram equals 1 milliliter. So therefore, our solution will have a mass, so M equals 100 grams. So we have 100 milliliters. It's mostly water, same density as water, so we're going to end up with 100 grams. Q equals MC delta T. M we know is 100 grams. C, we're going to be using the specific heat capacity of water. Okay, we assumed that in the question. And then delta T, we're going to be taking the temperature change from 24.6 and 21.4 degrees Celsius. So subbing in our numbers, we have 100 grams. For C, we have 4.18 joules per gram degrees Celsius for our specific heat capacity. Delta T is final minus initial, so 24.6 degrees Celsius minus 21.4 degrees Celsius. That's going to give us Q of our solution. I'm going to write that out. Q solution being, we just type all of that into your calculator. Make sure that you put this in brackets so that you do your bed mass properly. I'm going to give you 1,337.6 joules as the heat of the solution. Now, step number 2 is the solution is acting as almost like an absorbent for all of the energy that's being released from the reaction. We know the reaction is exothermic, so what the energy that's released is going to heat the solution up. Step number 2 is that Q of the solution is equal to negative Q of the reaction, because really we're looking to find how much heat is released in the reaction. Okay, and we can do that by seeing how much the water heats up. We know Q of the solution is 1,337.6 joules, which means that Q of the reaction is equal to negative 1,337.6 joules. So really you're just changing the sign. If the water is heating up, okay, that means that your reaction is releasing heat. Step number 3 is to determine the enthalpy, the change in enthalpy. So delta H is equal to Q of the reaction divided by the moles. So again, we're following the steps up at the top of the page. So step number 1 was to find Q of the solution using MC delta T, then find the Q of reaction, and then step 3 is to find delta H. So Q of the reaction divided by the moles. Now we need to determine moles of copper sulfate here because this is asking us, okay, determine the heat of the reaction in kilojoules per mole of copper sulfate. So we need to find N, so N is moles of CuSO4 to be able to solve into this equation and put in for moles there. So N of CuSO4 is equal to C times V. So N equals C times V, if you remember from your grade 11 solutions unit. We are given information in the question about the volume and the concentration of our copper sulfate. So we have 50 milliliters, which we need to convert into liters, and we have 0.3 moles per liter. So C times V is going to give us 0.300 moles per liter times 50 milliliters, which will be I'm kind of lost a bit of room here, times 0.0500 liters is going to give us 0.0150 moles of CuSO4. We can sub that number into this equation. So delta H is equal to Q of the reaction we found to be negative 1337.6 joules divided by, we're going to sub in the moles of copper, so 0.0150 moles. And that is going to give us negative 89173.33 joules per mole for this reaction. Now this is a really big number, and the question also asked us to find it in kilojoules per mole. So we need to convert this into kilojoules per mole rather than joules per mole by dividing by 1,000 to get kilojoules okay, which is going to give us -89, so -89 kilojoules per mole. Actually, it should be 89.2. We have 3 significant figures in this question. So 3 sig figs there, 3 there, 3 there. There's 3 all over the place. So -89.2 kilojoules per mole to get 3 significant figures. And finally, the question also asked us for the thermochemical equation. Okay, so we can write this in one of 2 ways. We can write our energy as a reagent or a product. In this case, because it's negative, we know that it's a exothermic reaction, so we would write it as a product, or we can add it to the end of our equation here. So here's our reaction equation. We could write plus 89.2 kilojoules to the end, or we can rewrite it out with our delta H statement at the end. So that would be CuSO4 plus 2NaOH gives us Na2SO4 plus CuOH2. And then we would just write delta H equals -89.2 kilojoules per mole at the end of the reaction equation. So there's one more example of this type of question, so you can see the steps one more time, and then there's some practice questions. So one more question just like the one we did, and then your practice questions for homework that you can do after that. This question I'm going to do in class, so just finish up to the end of the last practice question and we'll do this one in our Zoom class together. All right, see you in a few days.